Hello, and welcome to another session on sequential circuits. Today we'll look at sequential circuits called shift registers. In general terms, the register is a storage device, and in digital systems, a register simply stores digital or binary bits. An n-bit register will store n signals, whether they be zeros or ones. The implementation of a simple 1-bit register is shown here implemented using a D flip-flop. In this D flip-flop, when the reset signal and the load signals are both 0, the flip-flop will hold its value and store a digital bit. When reset is high, on the other hand, then the output will reset to a value of 0. And when reset is low and load is high, then the action or state will be that Q, the output of the flip-flop, becomes the value of D, and a new bit becomes stored in the register. The shift register is a special type of register that shifts information left or right, and from serial to parallel, parallel to serial, and so on. There are many different kinds of shift registers, many of which are implemented using the flip-flops we've discussed in previous sections. The serial input, serial output shift register, for example, has a single input, in, and a single output that we call out. The shift register simply transfers information with each clock cycle from the input of each D flip-flop or register contained in the register to the output, and finally through the sequence to the final output of the circuit. So in every clock cycle we shift a bit to the right using the serial in, serial out shift register. Let's take a look at what this looks like in implementation. The first thing to note here is that we're working with D flip-flops or storage registers, and that they're trailing edge triggered, as is indicated by the triangle symbol at the clock input. That means that if a change is to occur at the output, it will happen at the trailing edge of the clock signal. So let's take a look at what goes on here with this shift register. The output may begin at a value that we're not sure of, and we call that undefined or unknown, which is a bad state of being. The reset signal on the first trailing edge of the clock makes sure that the output goes to a known value of 0. So at the next trailing edge of the clock, it's free to change into another value depending on what the input to this third flip-flop is. Now what we note here also on the first trailing edge after reset, right here at this trailing edge of the clock, is that the input has now shifted to a high value, which means a high value will then transfer from the D or the input of that first register to the output Q. Now that change won't show up until at the output until we transfer it 2 more times or go through 2 more clock cycles. So at the second clock cycle here, we'll see the input transfer to the second output, and then on the third trailing edge of the clock cycle, we'll see that value of the input that we had way back here, a 1, finally show up at the output at that trailing edge of the clock cycle here. And then in subsequent trailing edges of the clock cycle, it'll continue to follow the value of the input, except lagging that input by 3 whole clock cycles. And the serial input, serial output shift register is useful for storing bits as they come through over time. The serial input, parallel output shift register has a serial input just like the previous shift register, but instead of producing only one output, puts outputs out now on multiple wires, which are called here out 2, out 1, and out 0. Again, this shift register is trailing edge triggered so that the signals, if they do change, will change on the trailing edge of the clock. And let's take a look at what that looks like. We have 3 outputs for the shift register. Out 2, which is the first output of a shift register, out 1, and out 0. Just like in any other shift register, unless the register is reset, The initial value or state of the outputs is unknown, so the first thing we'll do in this shift register is that we'll reset all the output values to 0. And then on subsequent trailing edges of the clock, we'll be free to react to whatever the input is and compute a new input of known value. So up until the first reset signal, the output is an unknown. We're not sure what it is. So to stabilize the whole circuit, we'll reset to ensure we have known values at each of the outputs. And at the first trailing edge of the clock, we see the reset is active, so the outputs will all go to 0. On the next trailing edge of the clock, what we see is that the input is now 1, and output 2 will go high to follow that input. On the next trailing edge, it'll continue to follow the input, and so on and so forth. And similar to the serial input, serial output register, the outputs will lag. Output 1 will lag that first output by a single clock cycle. And the third output, out 0 in this case, will lag out 2 by yet another clock cycle. And this gives us the output of the serial input parallel output shift register, which in effect takes the serial information or the time-dependent information contained in input or in and transfers it to multiple wires or a parallel output. A more complicated shift register is the bidirectional parallel shift register. And this shift register is capable of containing multiple functions and implementing multiple functions through the shift and the load signals. With shift and load having 4 possible input combinations, there are 4 possible functions of this bidirectional parallel shift register. In this example, the first is when shift and load are both 0. And in that situation, the 4 registers, register 3, 2, 1, and 0, hold their present values and ignore whatever the values of bit 3, bit 2, bit 1, and bit 0 are. On the other hand, if shift is equal to 0 and load is equal to 1, we perform a function called a parallel load. In a parallel load, bit 3 is now loaded into register 3, bit 2 is loaded into register 2, and so on for bit 1 and bit 0. In the 2 remaining functions, shift left and shift right, information is transferred to the left or to the right. In the shift left condition, the contents of register 0 are shifted to register 1, contents of register 1 shifted to register 2, and from register 2 to register 3. The value in register 3 now may be shifted to the output, and then register 0, what goes in here? Now that the value of register 0 is shifted to register 1, what goes on? Well, it depends what kind of shift left function we have. And one of the more popular functions is a logical shift, which means that the register that has been emptied will be reloaded with a 0. So in a logical shift, register 0 will be loaded with a 0 and hold a 0 until something else happens in the next clock cycle. In shift right, it's exactly in the opposite direction. The contents of register 3 go to 2, register 2 goes to 1, 1 goes to 0, and the contents of register 0 go to out. And register 3 again in a logical shift is loaded with a 0, so the new value in register 3 will be a 0 if we have a logical shift right. And we can have other types of shifts as well that define what's going to happen to that now empty register. So this bidirectional parallel shift register can shift information in both directions. It can do a parallel load or a serial load and can do a variety of different things in controlling the output. It's a highly multifunctional shift register. Shift registers are also very useful as counters. And a counter simply does what it sounds like. It counts in one direction or another. The simplest is the up counter that counts up from 0 to 1, 2, 3, 4, 5, 6, 7. And when it reaches its maximum capacity of its bit, starts over at 0. The down counter does exactly the opposite, starts at its highest value and goes down from there. And once it's done counting down, it just starts at its high value again and continues over. Arbitrary counters can be used to count any different sequence that's useful for the function at hand. As an example, let's take a look at the down counter implemented with a 3D flip-flop shift register. Here we have three different functions, three different flip-flops. Bit 0 will be our least significant bit of our counter, and bit 2 will be our most significant bit of our counter. And we can take a look at the timing diagram of this shift register to understand its function. So bit 0 is the output of the first flip-flop in the shift register, and just like all other shift registers, it needs to be reset to make sure what it carries is not an unknown value. In this counter, we're going to assume an asynchronous reset, meaning immediately when reset occurs, the output goes to 0 and stays there until a trailing edge of the clock occurs and reset is lifted. Now Q0 here, Q0 is the opposite of the output bit 0, so it will go from an unknown value to a value of 1. And then what bit 0 will do, since Q0 of this first flip-flop is fed back to the input D, is at every trailing edge of the clock cycle after reset is lifted, bit 0 will toggle. The output Q0 is the output of bit 0, so it will do the opposite and toggle in the other direction at every trailing edge of the clock cycle. And then bit 1, since it's being fed a clock created by Q0, is now going to react to the input D at every trailing edge of Q0. So instead of looking at the trailing edge of the clock now, we'll just look at the trailing edge of Q0. And bit 1 will also toggle at every trailing edge, but this time of Q0 rather than of the clock, and so on. And you can see here that we've effectively built a down counter. It starts out at 0, 0, then counts down to 1, 1, counts down again to 1, 0, then to 0, 1, then to 0, 0, and after that it will start the down counting process all over again. And bit 2 will do exactly the same thing, counting down now in 3 bits rather than just 2. So we've seen here that shift registers are not only sequential circuits, but they are fundamentally built on registers that store information. Shift registers then allow that stored information to be moved around, whether to be counted, to be converted from serial to parallel, or do a wide variety of functions that are possible within the sequential circuit design parameters we've talked about in previous sections. That's all today for shift registers. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.